Section 2.2, Polynomial Functions of Higher Degree. Today we're going to talk about graphs of polynomial functions. Graphs of polynomial functions have smooth turns, no sharp turns, they are continuous, and they have no breaks in the graphs. Let me give you a couple of examples of what your graphs may look like. They have smooth turns, something like this maybe, or something like this. No sharp points. Here's some examples of what polynomial graphs would not look like. No absolute values, no sharp points like that. No hyperbolas where there are two different pieces. I don't know if you remember what a hyperbola looks like. No piecewise graphs where you would have two separate portions. Just nice continuous curves. Something like these two graphs would be graphs of polynomial functions. So that's what we'll be looking at today. The first thing we're going to look at is the very simplest form, which would be a monomial function. Just f of x or y equals x to a single exponent. So that will be our first example. An even degree polynomial graph will be similar to a parabola. F of x equals x squared, a parabola. Oops, sorry about that. Try to get rid of that. Okay. An odd degree polynomial graph will be similar to y equals x cubed, your cubic graph. Remember, your cubic graph does something like this. And your parabola obviously is similar to that. Not a very good graph, but you get the idea. So any even degree monomial will look similar to your parabola, and even odd degree will look similar to your cubic. The higher degree, the flatter the graph will be at the origin. So let's sketch the graph of f of x equals negative x to the fifth. Okay, let's get us a graph going on here. We all know what the negative sign does in the front, but since this is an x to the fifth, this is going to be similar to, is it going to be similar to our parabola or similar to our cubic? Well, since it's an odd degree, it's going to be similar to our cubic, so it's going to be similar to x cubed. Since we have a negative in the front, it's going to be reflected. But since it's so similar to x cubed, it's going to be a little flatter at the origin because it's a higher degree, but it is reflected. Oops, reflected. Sorry about that. That should be an R for reflected. So it's similar to x cubed, a little bit flatter at the origin because the exponent is higher and it is reflected. And it doesn't have any other transformations. It's not moved left or right or up or down. So we have our center point right here at the origin, but it is reflected. So my graph would look something like this. Try to do a better job. Make it a little bit flatter here through the middle. Something kind of like that. Okay, now we still do have the point negative 1, 1 on the graph, and 1, negative 1 on the graph. Okay, just like your parent function would have the point 1, 1 on the graph and negative 1, negative 1 on the graph. This would have negative 1, 1 and 1, negative 1 on the graph. Okay, so the only thing that's different is it's kind of flattening out here in the middle. Okay, and as we work on these online videos, I'll try to make these a little neater. Sorry about that, and try to make these neater as we go on. So similar to x cubed, flatter at the origin, and it is reflected. So let's move on to the next one here. This one is x plus 5 to the fourth. Since it is an even degree, it's going to be similar to x squared. So this is going to be similar to x squared, but it's going to be a little flatter. I'm not really going to say at the origin because it's not going to be at the origin anymore. I'm going to say at the vertex, because with this plus 5, surely by now we all know that this plus 5 moves the graph which direction? Hopefully everybody is thinking that it's going to move to the left 5. So 1, 2, 3, 4, 5. Now it doesn't have any reflection or anything else going on. 1, 2, 3, 4, 5. And then it's going to be a little bit flatter, opening up, a little bit flatter here, opening up. And we will work more later about getting some nice points. Would be over 1, up 1, over 1, up 1, and so on. Over 2, up 4, over 2, up 4. And if I had a nicer graph, I'd put some more points on there. Over 1, up 1, over 2, up 4, and we'll put more points on there later. Okay, similar to x squared, flatter at the vertex, left 5. So that's how you do monomial functions, monomial polynomials, single degrees. Okay, now let's talk about the end behaviors of a graph. What does the left side of a graph do and what does the right side of a graph do? I'm talking about polynomial function graphs, the kind that does all kinds of curvy stuff in the middle. Now we did talk about this last year in Algebra 2. See how much you all remember. You know, we could have all kinds of graphs that do this. We could have some graphs that do this. We could have graphs, well, that's kind of the same thing. I'll get the picture. We could have some curvy graphs. We can have graphs that both sides point down. We could have graphs where both sides point up, or we could have some graphs where one side points down and one side points up. This box right here is the exact same box from the notes that we did last year in Algebra 2. So hopefully this looks familiar to you. I pulled this right out of our notes that we used from last year. So we want to go back over the rules that you need to figure out or use to figure out what are the ends of your graph doing. What's the left side doing? What's the right side doing? How do you figure out if the left side is going up or down, or if the right side is going up or down? And that's all based off of the degrees. Okay, it's all based off of the degrees. So we need to look at the degrees and figure out if we're dealing with odd or even. Now if you'll flip over to the next page, I'm going to come back to this box, so if you'll flip over to the next page of your notes, when I'm talking about degrees, I'm talking about the highest exponent. Okay, these are your degrees right here, the highest exponent in your polynomial. Is it an odd number or an even number? Okay, so back on our notes over here, even or odd, that's talking about the degree, if it's an even degree or an odd degree. If you have an even degree, even degrees go in the same direction. Right? Even degree graphs, or even degrees, go in the same direction, even degree exponents. So that means both ends would be up like this one, or both ends would be down like this one. Well, if you have an even degree with a positive coefficient, again, I'm kind of looking ahead at our next examples, like over here, even degree, and this coefficient here in the front is a positive number. So that would tell me, oops, sorry about that, let's go back. An even degree with a positive coefficient means that the left side is going to go up and the right side is going to go up. Even telling me the same direction, positive telling me up. Okay, even degree, same direction, negative telling me both sides will go down. Now, if both sides are going up, you know, I'm going to have some curvy stuff going on in the middle, and we're going to work on figuring all that out. I'm not worried about that right now. I just want you to be able to tell me what the left side is going to do and what the right side is going to do. We'll figure out all the stuff in the middle here in just a little bit. Okay, you just need to be able to tell me the left side is up and the right side is up, or the left side is down and the right side is down. So if even degrees go in the same direction, then you should be able to figure out that that means that odd degrees are going to go in opposite directions or different directions. So I'm going to put opposite direction here. If you want to put different direction, that's the same thing. So if you have an odd degree for your leading term, then the ends of your graph are going to go different directions, like this one. Or let me put another example here, like this one. Okay, left side up, right side down. Now, this is not slope, but slope may help you think about this. think about an odd degree with a positive coefficient. Think about a line with a positive slope. A line with a positive slope would look like this. What's the left side doing? It's going down. And what's the right side doing? It's going up. Okay, again, we'll have some stuff happening in the middle. We'll work on that in a minute. I'm just worried about the ends. Left side is down, right side is up. Odd degree, negative coefficient. Again, it's not slope, but that'll help you keep this straight in your mind. Negative slope. Think about a line with a negative slope. That's what it looks like. So the left side would be up and the right side would be down. And we'll worry about all this stuff in the middle here in a few minutes. So just like I told my Algebra 2 class last year, this is not a box that you have to memorize. Just think about it. It should be easy if you think about it. Even degrees go in the same direction. Positive is up, negative is down. Odd degrees go in different directions. If it's positive, think about a positive slope. If it's negative, think about a negative slope. And it's not something that you have to memorize this whole box. Just think about it. Alright, and one other rule here before we look over at the next examples. You need to know the maximum number of turns that a polynomial function may have. Look at all these little squigglies I put in here. The number of times that a graph can turn and change directions, like this one would have turned 1, 2, 3 times. It's all based on the degrees. Okay, it's your degree minus 1. So like a 5th degree polynomial, subtract 1 from it, that means it can only turn 4 times. Okay, so you would just take the degree and subtract 1. And we're going to use this, we're going to do some examples here in just a second. So, flip over to the next page and let's try some of these.